We are going to take a look now at the constitutive relationships of the C element and how it relates in terms of the different energy domains, the representation in block diagram, the representation in bond graph model. So we are focusing now on this element right here. So the C element is, you could say, perhaps if you remember it this way, the C element, we are going to call it the energy storing element. Energy storing element or storage element. See? Okay. So if we look at the different way we represent this, there is a couple of ways we represent the C element. Let's do it in the with the same color. You can have a C element that is like this. And you can have a C element that is like this. Even if the power goes into the element, you can have like this. You know, we're gonna put both of those in like this. What does it mean? It means that the effort in this case, the E, this is the effort variable, is the output variable. In other words, this is coming out of C. This F, the flow, this is in. In this case, you see, this is the flow is out, and the effort is in and out of the element. Depending on what is in and out of the element, then we will have one block diagram or the other. Just like we did with the R element, that the equation is different. In this case, you have a situation where in one form produces an equation in the integral form, and the other one produces an equation in the derivative form. So maybe what we should do is, well, draw a line in here so that we look at this in what I want is, in here is your bond graph. We need to put the block diagram and we need to put the equations. So this is your bond graph. This is going to be your block diagram. And these ones are going to be your equations. Okay. In this particular case, since the output is the effort, then it follows that you can say that the effort is equal to 1 over the element 1 over c, the integral of f dt. This is what this means. It means that the output effort is 1 over c, the integral of f dt. Or you can write this also as 1 over c times q. Okay. And it follows from this that df dt if you differentiate this, yeah, df dt is equal to, yeah, E is equal to 1 over c times q. No, dq dt is f. There we go. So how does this relate to here? You have that towards the element, you have that this, if this is the element in here, see the C element is in here. The effort variable is the output, and the flow variable is the input. So what does that have to do to to F to produce the effort? You have to, let's see how we do this. This is, we will have to integrate once by using 1 over s, and then you have a, we could write it like this, and then it goes the opposite here, multiply by 1 over c. So this block diagram corresponds to this equation right here. But if you have a this kind, it is different, completely different. We're gonna put the element in here. Do you see the effort is going in, right? So this variable is going in and F is coming out. Okay, so with E, you see, let's just play now with this equation in here. For this to write as an output, now F would have to be C times dE dt, right? And so it follows that since the QDT is equal to F, you can say since dQ dt is equal to F, consequently, you have that dQ dt is equal to C times dE dt. Do you see now? I'm going to use a different color to emphasize something that is really obvious, but this is obviously the integral form. Yeah, but this one right here is the derivative form. There you go. So if you have the equations this way, then obviously you need to describe it in a graphical form. In this particular case, E before gets differentiated by the variable S, and then you put it using the Simulink notation, multiplies by C, and now this comes as F. See? So this block diagram corresponds to the integral form. This block diagram corresponds to the derivative form. And I think it is left to, what is left to do here is that I need to show you examples in the different energy domains. Like for example, we do a mechanical system. In this case, very easily we could just represent this as a spring, like this, where you have the force, to stretch it out. And you know in here that the force is equal to K times X. But I am going to emphasize the equivalence, because this is something that is important. This form is like E is equal to 1 over C times Q, where the F corresponds to the E variable and X corresponds to the Q variable. You see? So this is the element, and the way we write the equation is in the integral form. So that is in the mechanical domain. I believe that the second one that we were doing is to draw it in the electrical domain. Okay. And so this would be the equivalent of having a circuit like this with a capacitor like this, the C element with value C. And in here, you are going to say that the voltage of C is equal to 1 over C times the integral of I dt, or 1 over C times Q. That equation is like V sub C V sub C is well, I put both of those in there, but what I meant to put is in terms of the generalized variables. I will just write down in here, because this is like writing E again is 1 over C times the integral of 1 over C times Q for the electrical domain. This one here, if you want to write it in the integral form, this is like saying the force is equal to K times the integral of dV dt, like this. I don't mind you write like this, K times the integral of V dt, like this. Same thing. Yeah? So right now we're trying to work with the different velocities, with the different conditions. Oops. Well, let's leave it alone in there. In the hydraulic realm, you have like a tank in here, which is a storage tank, where you have Q and then you have this tank like that. And here you know that the pressure is equal to, in this case, the constant also 1 over C, the integral in this case of Q dt, Q being the volume flow rate. But if you write it as 1 over C times the volume, C, and that you have that in this case you have that E is equal to 1 over C times Q. And we'll do one for the rotational one, for a torsional spring, like this. This is going to put it in rotation. And if you have something like this that is like let's see how we represent it in terms of a torsional spring. Well, maybe we'll do it this way. One where you put the moment in here, like this. So in here you have that T, the torque, is equal to the stiffness in rotation times the angle of twist, or this is K times the integral of omega dt in rotation. And this is the same thing as E is equal to 1 over C times Q. What is important is here that the derivative, in this case, the dx dt, in this case is the flow, which would be the velocity in here. In this other one, the q dt, this is the current. And in this one, again, is the dv dt is equal to q. And on this last one, you have that d theta dt is equal to omega. So this way you have the representation of the energy, different energy domains, and we have seen the bond graph representation in integral form and derivative form, the block diagrams, and the corresponding equations, and as they relate in different energy domains.